time for us to do some practice involving comparisons. In particular, we're looking at infinite series, and we want to answer the question, do we have something which converges? In other words, it's a finite value when we add everything up, or does it not converge? And what we do is we say, look, there's a handful of series which we do know the answer for. So instead of trying to figure out everything new every time, we say, well, let's compare it to things that we already know. And perhaps, if we make a good comparison, that'll suffice. Now, the key, of course, is learning to recognize what do we compare things to, how do we run the comparisons, and that comes with practice. So make sure you're doing practice. If you're following along with the video, make use of the pause button. If you see a problem, try it yourself first. See what you can figure out, and if you ever need to compare, no worries. I'll be right there for you. So, let's begin. Our first problem. Does the sum from 1 to infinity of 1 over root n minus 0.5 to the n converge? All right. So, what are we going to do? Now, we can run a couple of tests, right? Because we're talking about comparison tests. There's actually two of them. There's the just straightforward comparison test. Sometimes people call it the basic comparison test. And there's limit comparison test. So we can do both. Now, before we start, though, we kind of want to get a feel for what do we think the answer is. In other words, before we start answering the question whether it converges or diverges, we're going to try to look at it and say, this is what we think it is. Now, the reason it's important to have an early decision is it will influence what we do later on. So how do you make a decision? Well, when you have a sum, what you do is you say, what is happening to the terms? How are they going to zero? In other words, can we capture the essence of how quickly it goes to zero? And so for that, we say, what's important? Now, upstairs, it's always 1. All right, fine. Downstairs, what do we have? We have root n and 0.5 to the n. Now, as n gets big, 0.5 to the n, yes, it's exponential, but it's not exponentially increasing and blowing up because 0.5 is less than 1. It's actually decreasing, going to 0, which means, look, for large values of n, this 0.5 to the n is inconsequential. It's basically meaningless. So we can kind of cover that up, say, look, it's more or less behaving like 1 over root n. Or if you like 1 over n to the half, we're like, p series, got it, good. And so now we're like, mwahaha, and away we go. Because we know about p series. So we say, okay, 1 over n to the half, that's p equals a half. Well, that's not bigger than 1, so it must diverge. So we think it must diverge. All right, so with that in mind, let's begin. So let's start with the comparison test. Now, because we think this is going to diverge, what we want to do is we want to say that this expression here, 1 over root n minus 0.5 to the n, is bigger than or equal to something which also is going to diverge. Now what we need to do is think about, okay, how can I lower bound it? Well, here's a good rule of thumb. If I want to make a larger expression, what can I do? Well, if I want to make a smaller, right, because I want a smaller piece here. If I want something to be smaller, make the denominator larger, right? Larger denominator, smaller value. So notice this is 1 over root n minus something. Well, look, if we just take 1 over root n, because that has a larger denominator, because this one subtracts something off, even if it's a small thing, it's still a subtraction, that means it's a smaller value. So now we say, great, this is a simpler thing to compare to. Then we say, and the sum from 1 to infinity of 1 over root n diverges. So we know we have something below this. It diverges, and now our conclusion, great. We've bounded it below by something which gets big, so it must also get big, And therefore, our conclusion is that our sum from 1 to infinity of 1 over root n minus 0.5 to the n will diverge. All right, so that's what we would do if we were doing comparison. Now, what if we were doing limit comparison? We might as well see both. And limit comparison, we actually kind of already did. So what's the idea of limit comparison? Limit comparison says, hey, let's focus on I can spell comparison. Let's focus on the real essential growth. Or, as I like to say, let's get rid of the noise. So whenever I see something being added and subtracted, it's like, okay, we're going to throw out the smaller piece. So in our case, we say what? Well, we look at a sub n, which is 1 over root n minus 0.5 to the n. We say, well, here I see an added or subtraction. Which one is smaller? Well, the root n gets big, 0.5 to the n gets small, so that 0.5 to the n, that's the part which we throw out, because we keep only the biggest pieces. So we let b sub n equals 1 over root n. And now, if you always throw out the smaller piece, what's going to happen is that our limit, as we head to infinity, of an over bn will be 1. Now we can do this properly and say, look, this is the limit as n goes to infinity of 1 over root n minus 0.5 to the n over 1 over root n. And now you can do things, for example, one thing we can do is we can move this 1 over root n up. So it becomes a root n up here. And then we can imagine multiplying top and bottom by 1 over root n. And if you do that, it becomes limit as n goes to infinity of 1 over 1 minus 0.5 to the n over root n. And this will always be the case. See, if you keep your highest terms, the largest terms, when you divide out by the growth of the largest term in the piece, you have 1, and then this thing is smaller. So that goes to 0, which is 1. So that says in the limit, an and bn are essentially the same. Of course, you have to go far enough away. And now, the only thing we care about is it converges to something. And then we say, great. So that says we can tie the two sequences together. If one converges, the other converges. If one diverges, the other diverges. So now we've said, this says you've done the tying. We also have to say that the sum from 1 to infinity of 1 over root n diverges. And we should be explicit here. It's because it's a p-series. We didn't write it down before, but we should have said that up there as well. And so, since they're tied together, our conclusion is that the sum that we're interested in also will diverge. So there we go. That's the basic idea. Now, in terms of actually implementing this, in practice, if you get to the habit of saying, look, I only keep the highest growing terms, then it will always be the case that this limit goes to 1. And then you say, great, I just have to understand what the sum is of the stuff that's left over when I remove the lower terms. All right, well, good. 1 down. We still have more to do. Plenty to do. Plenty to do. Okay. Now, the question. Does the sum from 1 to infinity of 1 over n plus 2 to the n converge? All right. So, again, we like to sort of answer the question before we begin. And so, really, most of what we're focusing on is the justification. So how do we answer the question before we begin? Well, what we do is we look at it and say, hey, I see pluses. So let's think about what's the dominant term. N versus 2 to the n. And when we look at this, we say, well, n, okay, that grows, sure. But 2 to the n, whoosh, exponential. Yeah, 2 to the n is going to win the race by a mile. Okay, so 2 to the n is the dominant term. So we would imagine, oh, cover that up. It looks a lot like the sum of 1 over 2 to the n. In other words, it's a geometric sum where what our ratio that we multiply by every stage, is a half. That's going to converge. Okay, so we think the answer is yes. All right, so now that we think the answer is yes, we can say, all right, let's think about the comparison test. Because we're thinking the answer is converging, what we want to do is we want to get this below something. Okay, so how do we get it below something? Well, larger denominator, smaller value. Since everything's being added, it says, look, just throw away one of the terms. So we say, look, we're going to throw away the smaller term. It's always important you keep the largest terms. The largest terms are going to tell us behavior. And that's what we're interested in. So now we say, hey, that's fantastic. Technically speaking, we should also say this is greater than or equal to 0, but all right, that's easy to check. And we have that the sum from 1 to infinity, this is 1/2 to the n, converges. We even know what it converges to, but that actually doesn't really matter. The value that it converges to doesn't really help us. So the conclusion is that the sum from 1 to infinity of 1 over n plus 2 to the n, which is below this, but also not negative, right? So it has to be something finite, so it must converge. Now, on a side note, what could we have done? You could have said, hey, Steve, hold on a second. Couldn't we have said 1 over n plus 2 to the n is below 1 over n? And the answer is yes. That's totally 100% true. Absolutely. But where are you going with this? Okay. And look, check this out. The sum from 1 to infinity of 1 over n diverges, Steve, right? Oh, yeah. It's true. So what's the conclusion we can make about that sum? The answer is no conclusion at all. Why? Well, because what's happening is it says, look, I have something which diverges, but now I have something beneath it. And the problem is, just because I'm below something which diverges doesn't mean I have to diverge. I could also converge. So this here, this is no information that we gain. So we haven't learned anything. So this is why you really want to pay attention. It's not just like, oh, I'll just drop any term I want. No. You want to make sure you drop the lower terms. Pay attention, because otherwise you might get misled and say, oh, well, okay, it looks like it's 1 over n, diverges. But that's because you're not paying attention to the real thing that grows, the 2 to the n. Now, what if we did this by limit comparison? Well, okay, what would happen then? Well, what we would do is we would simply say, all right, we'll let a sub n equal what we currently have, n plus 2 to the n, and we'll let b sub n, okay, knock out the lower order terms, 1 over 2 to the n. And now we say, okay, look at the limit as n goes to infinity of a sub n over b to the n, b sub n. Now, it will be the case, as long as you do this properly, that when you knock out the lower order terms, this is going to go to 1. And if it doesn't go to 1, you didn't knock out the lower order terms. So why? Well, because, and again, I'll say this a couple of times, and hopefully we'll be like, okay, all right, I'm convinced. What happens is really what you should think of is the effect is like I'm dividing out by the highest terms, right? So if you rearrange this, and this is a little bit of not too bad, it becomes n over 2 to the n plus 1. So, there's a little bit of work to get from here to there, but it's just algebra manipulation. And now we say, that goes to 1, which means that they're tied together. Whatever one does, the other does. And since we also have to say, well, great, you've tied them together, what does the other one do? Well, it converges, and we have to say, why does it converge? It's geometric. It's a geometric series, and we have that r, which is a half, is less than 1. So our conclusion is, since they're tied together, that's what limit comparison test says, hey, whatever one does, the other one does as well. We come to the conclusion that this sum also converges. And there we go. Done. All right. Well, these aren't so bad. We're kind of getting the hang of this. Well, let's keep going, right? More to do. More to do. Okay. Does the sum from 1 to infinity of 1 over n squared plus sine squared n converge? All right. Well, what can we do? What can we do? Well, let's, we've done a couple of these now, so let's just say, look, what's going on here? Between n squared versus sine squared n, which one's important? Well, the n squared is going to get big. Sine squared is not, right? Sine squared, see, sine oscillates between plus 1 and minus 1. Sine squared actually oscillates between 0 and 1. Okay, so what does that tell us? Well, it tells us, look, this part is sort of unimportant because it's bounded between 0 and 1. And so, as I go to infinity, it's the n squared which dominates. So we say, okay, so this looks like 1 over n squared. All right, great. And we know 1 over n squared is a p-series, converging. And so we already know the answer is yes. We have to justify it now. And, well, we don't need to do both tests. And so the question becomes, well, let's pick a test. Looks like we can probably do a pretty simple comparison test, right? Well, why? Well, we think this converges. So we say, all right, we want to find something that's above here which converges. Well, what's something that's above here which converges? Well, we go back to our philosophy, right? Larger denominator, smaller value. So if I want to have something here, I say, oh, I should make a smaller denominator. So I should remove something. Well, I want to remove the thing that's not important. The sine squared n is not important. So we have the following. 1 over n squared is an upper bound for 1 over n squared plus sine squared. And now we're like, yeah, that's true, right? Because this adds a little bit, so small the denominator. So we got great. And of course, everything here is non-negative. And the sum from 1 to infinity of 1 over n squared converges. And we can say, why does it converge? It's a p-series. And here, p equals 2, which is bigger than 1. So, by the comparison test, our conclusion is that the original sum that we have here, 1 over n squared plus sine squared n, also converges. And you can do a limit comparison test. It's going to be very similar. All right. Well, wow, these are pretty quick. It's kind of nice to start a problem and say almost instantly, yes, here's the answer. And then you just have to write down what's going on. All right, question. Does the sum from 3 to infinity of 1 over n to the 0.99 plus a big number? Oh, boy, that's almost too big. Let's see. Can we figure out what that number is? If we add some commas here. Ooh, that is a big number. That's 1 billion. Wow, 1 billion. Wow. The denominators, you're always dividing by 1 billion plus something. And this something's getting pretty big as you head off to infinity. It's getting infinitely large. Well, what do we think? Now, you might say, ooh, Steve, I don't know here. I don't know. Starts at 3, and everything else we've done so far starts at 1. Should I be worried? No. It's okay that it starts somewhere other than 1. Really, it's not the start that determines whether you converge or diverge. It's the tail. As you go off to infinity, what's happening down there? So you can ignore the first billion terms, first trillion terms, whatever. It's that part which matters. Okay, so since that part matters, what do we think the answer is? Well, we look at it and say, there's noise, right? Because there's addition. So what's going to change more? A billion or n to the 0.99? So, billion is pretty big. N to 0.99, not that big at first, but it starts to get bigger and bigger. And eventually, in the long run, this dominates. Okay, so cover up the part that doesn't dominate. Ooh, it's so big, I need to... Okay, there we go. Does that converge or diverge? Well, what is it? It's P series, and P is 0.99. That's not bigger than 1. It's below 1. All right, so we think the answer should be diverge. All right. Now, with that in mind, we're ready to start. Can we try a comparison test? Well, if we tried a comparison test, what would we need? Since we think it's going to diverge, what we'd have to do is make a comparison to show this is bigger than or equal to something which diverges. Now the problem is, you say, oh, throw out the billion. Well, the problem is if you throw out the billion, you get n to the 0.99 is an upper bound. So it's not so easy to say, oh, what does it compare to? And in particular at the start, it's kind of hard to make a comparison because the terms are so teeny tiny. And so it's not so clear what comparison to make. Now there is a comparison. It's just not easy to find it. So that's okay. We learned many things, right? We learned many things so that we could be adaptable and work in any situation. So let's look at the limit comparison. And really, when we were making our decision, we really were running a limit comparison, so we know how it works. So we have a sub n, that's this original expression. So then we have our b sub n. Well, for that, we say, look, throw away the small term. And of course, when we say the small term, as you head off to infinity, not for like, ooh, what's small now? The start doesn't matter. It's the end that will decide. All right, great. And now we say, okay, that's the right comparison to make. You've captured the rate of growth. That's what you want to do. In essence, the question of converging, diverging, how fast are we growing? Or more appropriate, how quickly are we going to zero? And if we can figure that out, we can say yay or nay. Now, take a look at the limit as n goes to infinity of a sub n over b sub n. Well, what's equivalent to having done this, pulling out the lower order terms? It says, well, one way you can think about it, all right, let's just do it here. So we have 1 over n to 0.99 plus a billion. At some point, we're going to not go through and fill in all the details here. And then you have divided by b sub n, which really, okay, divided by b sub n multiplied by the reciprocal. All right, that's really n to the 0.99 over 1. But what we really want to do is multiply by, whoops, there we go. If we carefully rewrite, it's equivalent to saying, hey, I'm going to pull out the rate of growth on each term and just see what's going on. So when we do that, because the rates of growth are the same in both, the lower order terms are going to be the parts that are left, but you'll see that they now have the form small thing divided by large thing, which goes to 0, and therefore it goes to 1. So as long as you capture the right rate of growth, you're great. It's going to work. So make sure you're capturing the right rate of growth. Okay, so now we say, aha, we've linked them together. So we've linked the series together. We haven't answered the question yet. All we've said is the answer to one series, whether it converges or diverges, is the same as the answer to the other. So we also need to add, and the sum from 1 to infinity of 1 over n to 0.99 diverges, and we know that because p series. It's a p series, p equals 0.99, and that is less than or equal to 1. So if I have n to the p, and p is less than or equal to 1, it diverges. All right, so the conclusion is that our original sum, whoops, I just need to start at 3. Our original sum, 3 to infinity, of 1 over n to 0.99 plus a billion also diverges. And we are done. Good. All right. Well, good. In some sense, I really think limit comparison is the more powerful tool. I don't want to say, oh, forget comparison, it doesn't matter. There will be times when comparison test, it's the easier test to apply, and that limit comparison doesn't really work. But by and large, it's the limit comparison test that you want to use, because that will help you figure things out. All right, great. Well, keep going, right? More problems. All right, on to our next one. Okay, we'll kick it up a notch. Whew. Okay, does the sum from 100 to infinity of 5n plus log n plus 200 divided by 3 log n minus 5 cubed times n squared minus 0.2 to the n plus 20 converge? What? Oh, this is crazy. Wow, cool. All right, now, a couple of side notes. You might notice, of course, here it says start at 100. No problems. It's okay. We don't care where we start because that's not where the question about whether we converge or diverge is answered. The question about convergence or divergence happens up here at this end, at the infinity end. That's the part that matters. So, okay, don't care about where we start. Now, when we see a problem like this, we shouldn't panic because we say, hey, we've got the right tool. The right tool for us is limit comparison. See, limit comparison says get rid of all the noise. So, what do? Well, we're going to think of this piece here as our a sub n. And now we say, okay, we need to find another series where we have some b sub n, which is similar, and in the sense, right rate of growth. So, how do we start? Well, what we do is we go through and we remove anything that's being added or subtracted. We say, okay, what's the dominant part? So, let's start with the numerator. We have three things, 5n, log n, and 200. Between these three things, which one is bigger, the 5n, log n, or the 200? And when we say which one's bigger, as we head off to infinity, well, the answer is 5n. That's the dominant term. All the other terms are lower order. So we can say, all right, look, this numerator, we can think of as 5n. All right, how about the denominator? Well, let's just handle these two pieces separately. 3 log n versus 5. Which one matters? Well, the answer is the 3 log n heads to infinity, the 5 doesn't. So the 3 log n is going to drive the growth of this term. So this is the same as 3 log n to the 5th, where when I say it's the same as, the rate of growth behaves the same as that. And downstairs, there's a second term. There's n squared, 0.2 to the n, and 20. Okay, so you have three terms again. Which one matters? Well, n squared gets big. 0.2 to the n actually gets small, goes to 0, and then 20 just stays at 20. So it's the n squared. Whoops. Why did I write 5 there? That should be a 3. Sorry about that. I got transcription errors. I hate those. Okay, so there we go. Now, you can clean this up a little bit. You don't really care about the constants. You could ignore the constants if you want, or you can keep the constants in. It doesn't really matter. So you can think of this as 5/27 times 1 over, so you can cancel single n times log n cubed. All right, great. So what's happened here is we said, hey, a sub n and b sub n really behave the same. And in particular, we have that the limit as n goes to infinity of a sub n over b sub n is 1. Now, on a side note, let me try one more time to illustrate how you can think about why this works. So let's think of it in a slightly different way. So we're going to think of starting with our original expression. So 5n plus log n plus 200 divide by 3 log n minus 5 cubed and n squared minus 0.2 to the n plus 20. And what we'll do is in each piece, we're just going to factor only the largest term out. And we'll leave the smaller order terms in. So what are the larger terms? Well, they are the 5n, the 3 log n, and the n squared. So we're going to factor them and pull them out to the front. So we have the 5n. Downstairs we'd have 3 log n cubed and n squared. Now this might look familiar, right? This is our a sub n, and this is what we said, oh, that's what we're going to choose b sub n to be. What's left? Well, when you pull out the highest terms, well, you're going to have 1, where you had the highest term, and then the other terms get divided. So log n over 5n, 200 over 5n. Downstairs, it'll be 1 minus 5 over 3 log n cubed, because we pulled out 3 log n. And then it'll be 1 minus 0.2 to the n over n squared plus 20 over n squared. And the key thing here is this part right here. This is our a sub n over b sub n. And what do you see? When you look at it, you say, oh, hey, these pieces are all going to be 1s. And then everything else, because we divided by things which were higher in terms of the rate of growth, these all go to 0 as you head off to infinity. And therefore, we say, we see that a sub n over b sub n is 1. So that's why we say pull out these highest growing terms, and that will really determine what's happening. Okay, so we're not done. We're only like halfway, but I wanted to really illustrate with a more interesting example of why things work the way they work. So now, what can we conclude? Well, so we need to consider the following sum. The sum from 100 to infinity, and the constant doesn't really matter. What really matters, of course, is this n over log n cubed. That's going to determine. So what we've come to the point here is we have, hey, if this sum converges, our original sum converges. And if this sum diverges, the original sum diverges. All right, well, great. So we've said, what happens to that? Now, you'll notice this seems like a much nicer question than that question. So limit comparison is a great way to like whoosh, get rid of the noise, right? Reduce it way, way down. We like limit comparison. Thumbs up. Gets our seal of approval. but we still have to make this decision. And now the problem is, look, limit comparison won't work because we really stripped out all the noise. Now we start thinking, okay, what other tests do we have? It's not a p-series because of that log n. And we know it's kind of close though, right? Because we know 1 over n diverges. So this is just somehow slightly squeaking underneath because log n is pretty small compared to n. The question is it enough? And how do we make that decision? So to make that decision, we think back, okay, what kind of test do we have available to us? The integral test. So the integral test is almost tailor-made for this kind of sum. Why? Well, let's take a look. So if we look at the integral 100 to infinity of the 5/27ths, and again, the constant doesn't matter. If you want to get rid of the constants, no worries. 1 over x log x cubed dx. How can we do this sum? This integral. Well, what we can do is substitution. U equals log x. All right, so what does this become? We get log of 100, some number, and when you think about infinity, well, as you plug in infinity, well, it really means as you head to infinity, you go to infinity. So you get 5 over 27. Great. Now, the log x just makes sense because there's log x cubed. So there's a 1 over u cubed. But also, we should have said, hey, du is 1 over x dx. See, there's a 1 over x dx. So that's a du. And now, we're like, hey, this is an integral we can do. It's 1 over u cubed. No way you could do the integral of 5x plus log x plus 2. Forget it. Forget it. Hopeless. Hopeless. But because you take out the noise, there's hope. And things work out really nicely. All right. Well, we do this integral. Okay, so 5/27 is a constant. Think of this as u to the minus 3. Integral would be u to the minus 2. And then there's a minus a half that you have to, because of the exponent. And evaluate from log of 100 to infinity. But the important thing is, what happens as you go to infinity? It goes to 0. So this is some number. We don't really care what the value is. We could plug it in, and of course, and do it. But the important thing is it's finite. So this sum here converges by the integral test. Sorry, that's the work we just did right there. So we said, hey, this original sum will be tied to this sum. That's the limit comparison test. So whatever this sum does, that sum does. And this sum we said, okay, we applied the integral test, and that sum converged. So our conclusion is that our original sum also converges. So by limit comparison test, plus the integral test, this sum converges. Now notice we actually ended up using 2 tests. So you should be careful, and you don't want to fall into the trap of saying, oh, there's like a box here called integral test. There's a box here called comparison test. There's a box here. And you're like, I can only work with one box. You can sometimes get some cross-pollination of ideas. So be flexible. Be open to the possibility that you might have things coming together. All right. Wow. This one is fun just because it looks hopeless. And then it's like, oh, there's hope. Of course, we always want to have hope. That's a good thing. All right. Well, let's do one more. One last problem to finish up for this session. Determine whether the sum of square root n squared plus 1 sine squared of 1 over n from 1 to infinity converges. Okay. Wow. So what are we doing here? Well, I mean, it's a yes or no question, right? All the problems today are yes or no. Does this converge? Does it not converge? So let's not try to do a straight comparison test. Let's do limit comparison test. Now, when we're doing limit comparison test, the real question is, what is this behaving like? And if we can understand that, then questions like this are not so bad. So let's just think about our pieces. The square root of n squared plus 1. Well, what is it behaving like? You see there's an n squared plus 1. Whenever you see a plus, you're like, okay, throw out the lower order term because that won't matter in the long run. That's the plus 1. So this is about n for n large. Okay, so that says that's really behaving like n. Now what about sine squared of 1 over n? What is that doing? Well, one thing to think about is what's happening here. 1 over n is very small. So it's like we're trying to understand what's happening to sine squared when we plug in small values into the function. Now, if you think about the sine squared function, and of course, I'm sure many of us do as we lie in our beds at night thinking, wow, what does sine look like? Actually, let's not do sine squared. Let's just do sine. Okay, so sine would do this, right? There's the sine function approximately. And what's true? Well, if you zoom in near 0 and look at the tangent line, you'll see the tangent line is very nice. So the tangent line, it's very easy to compute, is the line y equals x. Now remember, there's this philosophy that the function mimics the tangent line near the point of tangency. So when we're near x equals 0, our conclusion is that sine of x is about x. So this is near x equals 0. This is, again, going back to our Calc 1 days. And, oh, yeah, function behaves like tangent line near the point of tangency. Well, 1 over n is near 0. So we can say, oh, this is behaving like 1 over n squared, right? Because that's the sine squared. All right, and again, this is for n large. So if we put these together, we say, all right, well, it looks like this is going to behave like 1 over n times, n times 1 over n squared, which is 1 over n. All right, well, do we think that should converge or diverge? It should diverge. It's a harmonic series. We know that diverges. And we're almost done. We just got to finish by, going through and dotting all our I's and crossing our T's. So what's going to happen here? So we say, okay, now we're going to let this a sub n equals square root of n squared plus 1 sine squared of 1 over n. And b sub n is what we've figured out. This is our 1 over n. And we're going to argue the limit as n goes to infinity of a sub n over b sub n is somehow a nice value. If we've done our job right and grabbed out the right rates of growth, it should be some finite non-zero number. And this is the hard part. Okay, so this is the limit n goes to infinity of, well, we have square root n squared plus 1, and then sine squared 1 over n. Divide that by 1 over n. And now, here we start thinking, okay, let's sort of do what we do here. One thing we can do is we can pull an n out of the square root. So this is the limit as n goes to infinity of n square root 1 plus 1 over n squared. There we go. Sine squared of 1 over n. Divide by 1 over n. And now let's move this n downstairs to join that n. And you might look at this and say, why are you doing that? What's your motivation? Well, we actually have a really good motivation here. And let me finish writing this down. So we still have that square root piece left. When this n goes down, it'll become another 1 over n. So it's like 1 over n squared. And I have a sine squared. So we can think of this as sine 1 over n over 1 over n squared. Now what's our motivation? Well, it comes back to the sine of x over x. One of the things that is known is if you take a limit as something, blah, goes to 0, of sine of blah over blah, you get 1. Well, that's because sine of x is behaving like x. So really it's like blah over blah. So this is a very famous fact from, you learn it hopefully in calculus at some point, if not before then. And we say, hey, check it out. These parts match. Blah, blah. That's right. Blah, blah. All right. And now they also are going to 0. And we say, so what happens is that this piece, as n gets large, goes to 1. And then here we say, all right, well, we get 1 plus 0 on the inside, so that's going to 1. So everything goes to 1. So perfect. We've now tied the original sum to the sum of 1 over n. So we just need to finish by saying, well, what happens to the sum of 1 over n? So we have, and since the sum from 1 to infinity of 1 over n diverges, and we can write down why. This is a harmonic sum, or if you like, harmonic series. And the conclusion is that by the limit comparison test, the original sum also must diverge. So there we go. So here we were like, wow, crazy looking expression. Does it converge? Does it diverge? And we just sort of dug into it, and we were able to say, oh, look, what is it really behaving like? What's the real rate of growth? And once we understood the real rate of growth, then we were like, aha, we know the answer, because it's behaving like 1 over n. Even though it looks crazy, when we pull out the growth, we say, it's behaving like 1 over n, and therefore we can answer our questions. So there we go. I like limit comparison test. It's a beautiful, beautiful test. Comparison test is also good. Make sure you know both. And the reason I really like limit comparison test is it helps in many cases to simplify your expression. I like to say it gets rid of the noise and just sort of says, look at the pure growth. How is it going to 0? And once you understand that, you can oftentimes figure out the answer fairly quickly. Of course, we need more tools, right? And we'll get them as we keep going forward. Thanks for joining. Hope you learned something, and I hope you keep practicing. And hopefully, there's a lot of hope today. We get to see you again. Bye.